question because I went through the MATLAB, um, at the labs that we did for MATLAB, and I was trying understanding KP, KD, KV, and KI. So this is the gains
Yeah.
and how they affect the system. Now, the first question I want to ask you, that the P, I know in the um, proportional integral PID and derivative, the KP stands for proportional.
Yeah.
So it does, right? It stands
Yeah.
for proportional. So it doesn't stand for position.
No. It stands for proportional to the error. So in the PID, usually the error is the signal that drives the system. So
Okay.
this KP stands for proportional gain, which means it is just a scalar multiple of the error signal, which is driving the motor.
Okay.
So in our
Uh,
thing, for our class, you should interpret or you should understand that KP is for proportional. Because if you, since you have gone through the labs, you can see that some of these circuits that you set up, some of them do not actually feedback the position. Some of them only feedback the speed of the motor. So
right.
you can even though you do that, you still have a KP gain. So it wouldn't really make sense to just say that the KP is just for position output, even though the confusion may arise. In this case, it would be you could argue that it stands for position because the in most cases you use the KP gain in a circuit where you feedback the position. So it may be the case that you may think that it is related to the position, but it is really not. It is related to the proportional gain.
Okay.
All right.
Can I share my screen, Professor?
Yeah, sure. Go ahead.
I believe I need your permission.
I think it's all. Let me see this. Oh yes. All right. Go ahead.
It's still disabled. Oh, here it is. Okay.
Yeah. Try again. It's
Uh, so here's a I have a picture of the board. So um, when we have the feedback coming back from example, the 360-degree potentiometer, which gives us the voltage which relates to the position of the motor,
yeah.
right? So then it feeds back here and it goes into the summing and error amplifier.
Yes.
So this right here, this feedback resistors, this one, and this one, if we connect them in parallel like this is what the gain is, right? This is what the KP would be, right?
Yes. It will be a scalar of that. Yes. In this case, it depends on how you set these resistors, right? Because if you choose the 100K feedback resistor, the gain will just be a negative gain, right? A negative one.
Right.
So you could argue whether this is the KP. So usually you see the KP in simple circuits. You see the attenuator knob you have right below the DC motor.
Yes.
Yeah, so you may remember that sometimes the output from the summing and error amplifier goes into the left-hand side of this attenuator, and
Yes.
then you actually use the signal coming out of the attenuator in order to drive the main control system. So you can use this knob as a figurative gain. So in order for you to dynamically increase the gain in the system, you cannot just be switching around the resistors in the error amplifier, right? You use this knob to figuratively actually increase the value of the signal going in terms of the proportional signal, right? So
Okay.
in some cases, in most cases, actually, this attenuator works as your gain. You see what I'm saying, Michael?
Yeah. So because this attenuator is from 0 to 1, right?
Yes. Yeah.
And so if the output is, for example, like 330K, so this it will be amplified by 3, and then
Yeah.
it goes here, and then here we can control the 3, like less than 3, and then all the way to 3, right?
Yeah. Yeah. So in a sense, because you start from a really low value, maybe zero point 0.5, right, which would give you a gain of, if you set the attenuator to a half, and if that is your starting position, you can actually understand how increasing the gain, or in other words, turning the attenuator all the way to 1 would actually that would correspond as increasing the gain in the simulations that we did in the MATLAB, right?
Yeah.
So the summing and error amplifier, right? This usually you want to use that just simply to create the difference or the error signal, right? Then you feed that into an additional component. It can be an attenuator, or it can be the circuit that you have in the middle of the analog controller, right?
Yep.
So usually, if you want to use the full PID, you want to use the analog controller elements. But if not, you set the attenuator to a low value so that you can have space to actually turn it to the right and therefore increase the signal going through the attenuator, and that will correspond to increase the gain. You usually don't fiddle around too much with the feedback resistor in the summing and error amplifier. If you remember that, you usually start at a value and then you leave that there alone, and all they ask you to do is just increase the attenuator.
Okay.
Which means more signal is going to go through as you increase the knob to the right. So that would correspond to actually increasing the gain. So if in the exam, everything is set up and I ask you increase the proportional gain, and if this signal coming out of the error amplifier goes into the attenuator, it would actually say it would actually mean turn the knob clockwise so that you can actually increase the signal going through the attenuator and therefore increase the proportional gain.
Could we also use the power amplifier to increase the gain?
I mean, that relates to the signal because you have a DC motor, you know from your previous experience that usually these things require high currents. So the power amplifier is actually amplifying the current that goes through the motor. So it doesn't really function as a gain per se, because you cannot really amplify how much current goes in through the motor, or only through the signal that you provide to the power amplifier. So the power amplifier will just simply amplify the current. It does not really serve as a dynamic gain that you can modify throughout the when your control system is operating.
Right. Okay. So it's not really gain; it's more just for more power for the motor to turn.
The power amplifier is there so that we can drive the motor.
Okay. Yeah, I think Mike said that to me when I asked him the other time. But you mentioned that the analog controller, when we're using the PID controller, the derivative and the integral gain, we would probably use the middle op amp for the proportional gain.
Yeah.
So would we be able to use we have to use that middle one when we're using the derivative or integral or both of them?
Yeah, usually in most circuits, the most effective signal without worrying about really some performance indices is the proportional signal. So usually, almost always, except in pathological cases or except in really sophisticated circuits that rely on some other kind of theory, you should always see some kind of proportional channel or signal or gain in your feedback system. This applies to really sophisticated feedback algorithms. There's always usually a proportional signal, because look at it this way, right? The whole goal, the ultimate goal of a control system is for the system to follow or to behave, as close as possible to a desired response, right? To a desired signal. So if you want this to behave, you need some kind of measurement to indicate how far apart these are. So this measurement comes from the error. So in your feedback system, if you want to minimize the error, you need a signal that is proportional to this error so that you can know exactly how far away you are from the desired position or the desired goal or signal. Well, it follows that every system, every feedback system where you are basing this idea on achieving a desired response, there must be something that relates to the error, and therefore there must be a proportional channel in there somewhere. So that is why in most of the labs that we do, actually in all of the labs that you built up, there's always a proportional channel. Do you see what I'm saying, Julian? You see how this comes out from the whole idea, from the initial idea of creating up a feedback circuit or a feedback control system? You see what I'm saying?
Yeah. Yeah, I think that makes sense. I think I was kind of wondering if you needed to use that middle circuit for the analog controller, or if you could use the summing and error amplifier on the left. But I think you answered the question that I have to use the middle one when you're using the PID controller, because you need the proportional gain as well.
Yeah, you actually need, you see, the whole idea is to reduce the error, right?
Mm-hmm.
Because if you reduce the error, that means that the output is equal or very close to the desired signal, right? To the desired trajectory, or to the desired position, or the desired speed. So the only way we can measure this is through the error, right? Because we know that they are equal if the error is 0. So the error signal is a very, very basic and fundamental quantity. That is why in your EE 371 course, the very first thing you defined was the error signal, because this thing is what is used to drive most feedback system, because the ultimate goal is to make one thing behave as close as possible to another.
Right.
So it follows that you should have some kind of error signal. Now, you introduce the derivative and the integral because the position, the proportional signal is not capable of dealing with most, loading cases that may arise in practice, right? You may have noise, you may have loading on the motor, you may have some kind of disturbances. So the proportional signal is just not enough to deal with most of the real life cases. So you introduce more sophisticated techniques to somehow supplement, the proportional channel. So that is why there should always be a proportional, and then you just add whatever you need in order to make the response a little bit better, to make it faster, to make it more accurate, and so on. Or basically, the signal driving this thing is the error, and that is why you must have a proportional channel in there. You see what I'm saying, Julianne? This relates to the whole idea of having a feedback at all, a feedback system.
Yeah, that makes sense.
So this goes back also to Michael's question as to why the KP doesn't really stand for position, because if the feedback is a speed, right? If the desired signal that I want to reach is a desired speed, I can feedback the speed, and the only thing I need to worry about is the signal, the error signal. So multiply the error times some gain, this will give you a proportional, channel, or a proportional signal, right? So this KP really stands for proportional as opposed to the position gain. You see what I'm saying, Michael, here?
Yep.
All right.
Now, Professor, I want to ask you, just although I know the definition of the 360-degree potentiometer, but I don't really think I understand what it means, because I understand that the 360-degree potentiometer will give us a voltage that is related to the position of the motor.
Okay.
But what does that mean? What position of the motor?
Do you have a picture of the mechanical unit of the thing, of the system that includes the motor setup?
Let me see.
Yeah, I could have opened this up. I thought you had some kind of picture from the.
No, that one I didn't take a picture of. No.
It's okay. It's usually at the very top of this manual. It's in the very first chapter.
Yeah. Let me see. It's this one.
Yeah, I keep scrolling up.
There it is.
That one. Can you maximize this thing and zoom in into the disc that you see right there on the right?
This.
Yeah, so that disc is a potentiometer, actually. Mm-hmm. So you see this arrow on the disc that has a thin line? Yeah, yes. That arrow. So that is the position of the motor, and you see this blue arrow painted on the top. So that's the reference. If this arrow points all the way up, or it matches this line, that means the voltage coming out of this is 0 volts, which means the position is at the 0 degrees. So this voltage coming out of the 360 potentiometer, the magnitude will tell you how far away you are from the 0 reference. So if the voltage is small, that means that the arrow is very close to the reference, which means that the position is very close to 0. As the magnitude grows, because remember, this system can give you negative and positive voltages, right? Negative means it is just away from the zero line on the negative direction or on the left direction, and positive, it means it's away from the zero line on the positive direction. So that is why I'm talking about the magnitude. So the magnitude or the magnitude of this voltage tells you exactly how far away you are from the zero reference. So if it tells you that the voltage coming out of the 360 potentiometer is 0 volts, that means you are right on the money on the zero line. I don't remember how far this thing goes, but I think it goes up to 1.5 or something like that in terms of the magnitude. So that is, in this case, in this system, 1.5 means you are, as far away as you can be from the zero line, which means you are 180 degrees away from the zero line.
Right.
Yeah, all the way there. So you see, this voltage that you get out of the 360 potentiometer has been set up so that its magnitude should tell you something about how far away this arrow is from the zero reference line. You see what I'm saying, Michael?
Yeah.
So this relates, so that is why this transducer, the very first things that I tell students is that this thing, this sensor, this 360 potentiometer, what I say is the following. This thing is producing a voltage which is proportional to the position of the motor, in a sense that it will tell you how far away you are from a reference line. In this case, the reference line is this little thin needle, on the top. Yeah, that's the reference line. So depending on how far away you are from this, the voltage will be larger in terms of the magnitude. It can be positive or negative, but it doesn't matter as long as the magnitude is non-zero. That means you are actually not on the reference line.
So the reference, I'm sorry. Yeah. So the reference line will be like, it's referring to the input signal. So it can be a square wave or a triangle wave, right? So that's telling you how far away it is from actually meeting or following.
No, but remember the whole idea. This voltage potentiometer will give you a voltage proportional to some physical characteristic. In this case, it will be position. So the voltage that comes in as the input, it will be a voltage, right? So depending on how much voltage this is, if it isn't zero, that means you don't want the position to be zero. You want it to be something else. So if the input isn't zero, that means you don't want the system to stay at zero. But if the input is at 0 volts, you want to stay the position to stay at 0 degrees or whatever units of you have chosen. So it really, this motor will align itself according to the magnitude of the input. So you see how this plays out. If the input, it's 1 volt, and you want this motor to behave as, to output 1 volt, it will, if the control system is designed properly, this voltage potentiometer will act up, or it should give you as close to possible as 1 volt, right? So this potentiometer will behave depending, on the input, on what the voltage or the magnitude of the voltage is. So basically, what you are doing in this feedback system is comparing voltages, right? A voltage can be proportional to anything. That is why this is just an example of this. In this case, the voltage coming out of this system or out of this disk is a voltage which is proportional to position, but it could be anything else. It could be altitude. It could be, what else? The position of an antenna. It could be some physical characteristic that has been mapped to a voltage. So you can think of this feedback system that we've been using as trying to match voltages. In the case of our system, the voltages have a physical explanation or a physical relationship because we have mapped them to position voltages or to position or angular positions, right? So you can see the whole idea behind this, the system that we've been using is we're just basically comparing voltages. Now you ask yourself, how do you get voltages? Well, you set up this transducer that transforms a physical unit into a voltage. So this is what all feedback systems rely on. You need a way to transform whatever physical characteristic you are trying to study or trying to manipulate into some voltage so that you can use circuits to compare the voltages and then map back to the original quantities. So think about this. What we are doing here is position feedback. You could use this as the altitude of an elevator or the attitude of an airplane, of the wings, right? The angular position of a wing. So this could be mapped to anything. What really boils down to this 360-degree potentiometer, it just gives you a voltage which is proportional to the position. Now your task is to provide the voltage that you want the motor to reach. So in this case, you should know what one voltage input should correspond to. I don't know if I'm making sense here, Michael. I mean, it's
yeah, it does. It's very good explanation
so
for
this,
sure.
This motor, this disc is just providing a voltage which is proportional to some physical, quantity, right? It could be the flux of a liquid in a hose. It could be the rate at which you roll steel sheets. It could be many things, right? It could be any kind of physical characteristics. The only thing is that you have to find a way to transform this physical quantity into a voltage so that you can compare it with the analog components that you know about, the electronics, right? So if you make this abstraction, you will realize that the whole thing we've been doing in the lab is just comparing voltages. If one voltage is equal to the other, that means that the error is zero and the feedback system has reached its desired position. And this is where the power amplifier comes in, right? Because this power amplifier knows nothing about what the feedback system is doing. It just receives the appropriate signal so that it can drive the motor. The higher the voltage that this thing receives, it gives you a proportional amount of current, right? So that it can drive the motor faster or slower depending on what the feedback system is actually dictating. Are we making sense here, Michael?
Yeah, it's very good. I have another question. When we use the type of generators, so this is where the velocity feedback would come back. So how come we need to use or in the labs, we always had it connected to attenuator, and we did not have the 360-degree potentiometer connected to attenuator?
Well, because remember how I introduced all of these techniques in the lab? You usually want to have your proportional signal, and then you want to see exactly what the effect is of introducing some kind of velocity signal. So we put it through the attenuator so that we can make it zero and then turn the knob all the way around so that you can make it non-zero, and so that you can understand with your own eyes exactly what is happening when you introduce this velocity feedback, right?
Okay.
So in our setup, we put it through the attenuator so that you can study it and so that you can compare the difference between having no velocity feedback, which means setting the attenuator to zero, and what happens when you make it non-zero, which means what happens when you have some velocity feedback, right? So in this case, it's just for studies purpose for us so that we can study it, so that we can know exactly what is the difference between having some and having none at all. Do you see what I'm saying?
Yeah. Okay. Yeah, it makes sense. I have one more question.
We did this in the simulations, right? Remember when at the beginning of when we were starting the semester, I would run the simulations only with the proportional gain, and then I would make the KV or the KD or the KI non-zero so that you could appreciate what it is that this thing does for you, right? You remember? So this is the function of this attenuator so that you can actually control it. And so you can decide whether introducing it actually improves the system or it doesn't, right? In this case, it does because we actually saw that it does, right? We just studied it. You see what I'm saying, Michael?
Yes.
Julian, you with us?
Yes, it makes sense.
All right. So,
Professor, can you spend like maybe 2 minutes if you still have time? I don't really understand the XY graphs. I have a trouble understanding what exactly it means.
Oh, the phase diagrams.
Right.
Okay. So think about it this way. Open up one of these. Yeah, this one's good. So look on the right hand side on the B plot, right? You see these diagrams. These we call them in research articles, you will see people call these time histories. Usually you call them graphs, or you call them square waves or waves, whatever this is, but this is just a time history of the voltage. So notice how these things are plotted. On the B side, you are plotting the voltages against time. For example, at the input at the top, you are plotting this square wave against time, and then the output at the bottom behaves just like an RC circuit that you know about, and this thing is plotted against time. You see the horizontal axis is time, right? You see what I'm saying? So now imagine, instead of plotting these two voltages against time, imagine plotting the voltages against each other. So that when you draw the picture, when you move on to the picture on the left-hand side, time comes in implicitly so that it traces the figure all around the X and Y plots. So the plot that you see on the left is actually a plot of these two voltages against each other, not against time, right? So I don't know if you remember, the plots on the left-hand side, the A plots, would be generated with a little like some kind of dot that would actually trace these things around as the motor was moving.
Yeah.
So this dot moving around, this is actually how this plot develops, over time. So time is still implicit in there, except that instead of plotting the signals against time, you are plotting them against each other. Now, how does this work then? Why is this thing useful? Imagine that you were to plot. I think I should share this so that I can. Can you stop sharing?
Yep.
I'm gonna share my. Can you tell me which page that was in the thing that you just showed me?
Yep. Let me check.
On the PDF, not on the document. Tell me the PDF page.
The PDF page is 117. Or the PDF page is 32.
Yeah, the PDF page, not the page on the manual itself.
Okay, I'm sorry. The page is 32.
32?
That's correct. Yeah.
Okay, yeah, I have it here now. Yeah, because you see this PDF pages do not correspond exactly to the manual pages. That's what I meant. So
okay.
You see this thing that you were showing?
Yes.
So these things are plotted against time. The voltage changes with time, and this is the same thing. So if you think about this, if you really try to understand how this plays out, this plotting these two voltages against each other will give you this. So now, why is this useful? Ask yourself how this plot would look if these two voltages were identical. If you were to have these two voltages against each other, and if they were identical, can you make a leap of your imagination and show exactly how this would look? Can you, Julianne or Michael, make a guess as to how this would look if you plot these two against each other and they are identical? Suppose I have two identical square waves here, or pulse trains, whatever you want to call this thing. And if they are identical and I make this plot where I plot the voltages against each other, how would this look?
Would it be like a straight line up and down?
It would be a straight line. So you can interpret these lines as the wider they are apart, that means the more different these things are.
Mm-hmm.
And the closer this thing is to a straight line, the closer these two things are actually in the time domain, right? As you see this arrow, time.
Yes.
Right?
Mm-hmm.
So if this line is not as wide, if this plot isn't very wide, if the eye, we usually call this the eye, if the eye isn't very wide, that means these two signals are very close to each other.
Is it a straight line, like diagonally?
Yeah, diagonal. Actually, it's a diagonal line, right?
Okay.
You can actually create a vertical line depending on how you what kind of inputs you have,
Mm-hmm.
right?
But if they're the same, then they're diagonal.
Any kind of straight lines here, but in this case, it would be a diagonal because in the x-axis here you have one voltage, and on the x-axis here you have another voltage, right? So it would be actually a diagonal from here to here. like that, or depending on how the polarity is going, maybe the other way around, or going across from top to bottom,
Mhm.
right, on the left-hand side. So he would actually be a diagonal here. But you guys understand what I'm saying, right? The closer these two things are to each other, the closer this will be to a straight line. It doesn't matter whether the straight line has a positive slope or a negative slope. It will be a slanted line over here.
Okay, and the y-axis acts as the voltage range.
Yeah, both of these will be voltages, right? This will this y-axis will be voltage, and this horizontal axis will also be voltage. Because remember, you are plotting these two voltages against each other, these two.
Right. Okay.
So if you are doing that, it follows that both of these axes should actually be voltages, right?
Okay.
So what I was saying before is time is still visible here, because if you remember from the lab, there's a little dot plotting these two things, right? These eyes or these plots here didn't just come up like that. You would actually see a trace or some kind of dot tracing them. So that is the time, right? That is how this thing implicitly shows the time when it isn't plotted through its own axis here. So this abstraction helps you to actually see how close they are to each other without looking at these two graphs separately.
So that kind of shows the error, right?
Yeah, exactly. Because if you see that this is closer to a straight line, that tells you that the error is smaller.
Mm-hmm.
So in other words, we usually call these phase diagrams because this relates to Hamiltonian dynamics. This is where the name comes from Hamiltonian dynamics as opposed to Lagrangian dynamics. But this is something else, right? The point is that these are called phase diagrams. In this case, we call them X and Y diagrams. But this boils down to another way of looking at the error. Because remember, the other way to look at the error is to compare these two, by inspection, or to actually compute the error signal using the board, and to actually plot maybe the error signal here at the bottom as a third plot. You guys remember when I asked you to do that in one of the simulations that I created, where I actually asked you to give me a plot of the error itself?
Yes.
So that graph would be a graph of the error against time. In this case, you see the error there implicitly, because the closer this thing is to a line, the closer the error will be to zero. So this diagram is helpful to understand this error from a different perspective. You guys see what I'm saying here?
Yep.
Yeah.
The lab usually in the lab, right? That is why I usually insist on students actually asking questions, right? So that you can ask questions as to how this, if you understand how to explain this, that means you are actually getting the most that you can out of the lab, right? I keep emphasizing this for all of you, right? If you ask questions, if you really try to understand what is being shown to you, the questions will come up naturally, right? You don't have to wait for somebody else to bring up the questions, because if you ask, or if you try to understand exactly what's being shown, the questions will arise naturally, just like they did for you now, right? As you were really trying to understand how this came about, the question, came up naturally.
I actually have one more question about this.
Okay, go ahead.
When we usually see the XY diagram, it's normally just one of these lines. You don't really see that other second one, and you see
it. It's only one of these. So that is why I said, depending on the polarity of these, right? Depending on which one you are plotting first, right? Or rather, which one is here? Is this is the x-axis the voltage corresponding to this one or to this one?
Gotcha. So depending on which way you're looking at it, like if you're plotting input versus output or output versus input.
Yeah. Yes, it will give you one or the other. So you usually don't see both of these. That's why one of them is like kind of a dotted line, right? Yeah. This one. So yeah, that's a good question, right? Because it may be confusing as to why you see these two when in reality in the lab you never saw both of them. So it just relates as to how you, whether it's input versus output or the other way around.
And so
essentially this boils down to the error. This is another interpretation of the error.
Okay. Yeah, that makes sense.
Does this make does this explain some of the figures you saw, Michael, when you look at it from this perspective?
Yes, 100%.
Yeah. So what else, guys? You have another some more things to discuss?
Yeah, I want to ask you a question because I noticed that when we were doing the last lab, when we actually used the PID
Yeah.
controller, we used the derivative channel, the proportional channel, and the integral channel.
Yeah.
But I still noticed that even though we used like the maximum amount of derivative gain, we had proportional gain, and we had the integral gain also like maxed. I still could see that there was an overshoot. There was a triangular wave, and there still was a overshoot over the transient, and then it would level out nicely. But there was still little overshoot.
Yeah.
And that's okay, right? Because we want to at least try to get it as perfect as possible. But that's as good as it's going to get, right?
Yeah, because you need to remember that this derivative and the integral action, these are actually complementary to each other, right? One of them will make the transient better, and the other one will make the steady state better, right? So
Right.
if you max them both out, right, one of them will try to fix what the other one is actually making worse, right? So these are conflicting actions when you max them out. That is why in PID you usually have something called tuning, where you use the ideal gains for the application that you want to have. Sometimes you care about more about rising time. Sometimes you care more about settling time. So depending on the application, you may want to use one more than the other, right? Or emphasize one action more than the other. That is why when you max them out, you probably will not see any kind of perfect behavior, because you are actually pushing this thing, in opposite directions, right? One of them will fix what the other is trying to make worse. You see what I'm saying here?
Yeah. Okay.
You want to tune it, fine tune it to whatever application you want to have. Let me give you an example. You may agree that, for example, the cruising system, you drive cars, right?
Yes. Mm-hmm.
You know what a cruise control is?
Yes.
So you may agree that the control system tailored for this cruise control should be somehow different than the control for an elevator, right? I mean, these two systems do not really have the same kind of dynamics, but you can actually use PID in both of these, but you have to really tune it to the ideal to your application, right? Because sometimes, for example, the cruise control, you want to
have KI, right? The integral.
You want to keep it at a fixed speed, right? You want you want to keep it at a fixed speed, right? So in this case, the integral would come more into play. Now, for example, in an elevator, you don't want these fast transitions where you have a lot of overshoot. You want to slow it down, and for that you use
KD
derivative or velocity feedback, right?
Velocity feedback, right?
Nice. Depending on the system that you are trying to apply this feedback on, you may decide to emphasize one action more than the other. You cannot just simply max them both out and expect the response to be the best possible. You see what I'm saying, Michael?
Yeah.
So when you look in terms of applying it, it makes sense as to why you cannot just really max these things out, right? Make sense, Michael?
Yeah, it's this week I feel like I allowed myself to really dive like deep into what exactly is going on here, and I'm very happy that I got to do that.
Yeah, I'm really happy that you did it too, because this class it can be very enlightening for people, right? When you really pay attention to what is happening, because you are controlling a physical thing, right? You are not dealing with simulations anymore. You are controlling a physical thing. You can learn more, a lot about make connections with other things you've learned in the past. Yep. Well, this only happens when you actually question the things that you are seeing. You remember how I said in the lab, a monkey could follow the instructions that they give you in the lab, right? You remember? Yes. I don't know if I said it in your class, but I meant it, right? Because I mean, any high school kid could follow the instructions and then just complete the thing, right? But you really have to pay some time. So I mean, or try to ask yourself whether you can explain what you are seeing. And then if you do that, the questions will come up naturally, right? I mean, so I'm really glad you got the chance to do this. And tomorrow you will see that this exam will be trivial for you because you know exactly what is happening. You will be able to answer any kind of questions that may come up.
I hope so.
So what about Julian? How are you? You feel okay with this? Has this helped?
Yeah, definitely did help a lot. I'm still going over a couple things, but I think I understand it a lot more now.
Okay. So I usually enjoy these kind of conversations in the lab, right? But some students, I can't really have these conversations in the lab because some students feel pressure to I don't know, to try to understand the thing, right? But you may remember that I usually walk around their classroom trying to, I ask you whether you're okay. I say something like this, but that really means, do you have something to talk about, right? In terms of the assignment, right? Most of the students in the class always say, I'm okay, I'm okay, I'm okay. And I say, okay, if you're okay, then you're okay, right? I can't really force you to really consider what you're trying to see here, right? But I try, and I'm always available to students, just like I did for you today. So I'm really glad that you got something out of this discussion because it's a cool class if you give it the time that it really needs to understand the concepts, right?
Yeah,
For
I mean,
sure.
it isn't a difficult class. You guys agree? I mean, this thing isn't quantum mechanics, right? But it is something so basic and so fundamental that if you understand it at an intuitive level, it will actually open up so many points of view uh, uh, of the world, right? Or something like that.
Yep.
All right. Any other question, guys?
Let me ask you one more question, Professor. Can I share my screen?
Yeah. Let me stop sharing mine so you can share yours. All right. Go ahead.
All right. So right here in the analog controller, we have another op amp here.
Yeah.
So after we go through the summing and error, and then we feed it here. So this is the feedback coming, let's say, from the 360-degree potentiometer coming here, and then we're gonna go here, and then boom, all of these channels are going this way. And then we have this other op amp here. Why do we need to have this op amp here? Why do we need to amplify this op amp?
In this case, this op amp serves really more for buffering because you are combining 4 different signals that come from very different op amps. You want to stabilize the thing, so we include this op amp there for stabilizing, for buffering the signal.
Okay.
And that is just more there for that because you see the gains are not very different, right? You could make this a gain of 1, or you could just boost it up a little bit if the application requires it, right?
Okay.
You can think of this op amp as a stabilizer op amp so that you can have more robust signals coming out of the full PID.
Beautiful.
There's a lot of I don't know if you remember your electronics courses, right? You usually you want to design stable circuits, right? When you deal with op amps, you check the stability of these things, right? So really, it boils down to the stability of the analog controller, right? You want the system to behave properly, so we include some kind of buffering here and there, some kind of stabilizers. So this is what this thing mainly does here.
Okay.
We cannot really go into such details as to how these op amps are designed in the background, right? But this is something that you should know from your previous courses, right? From your
Electronics
experience, right? But that's mainly there for just exactly for that, so that you can combine these signals in a more stable way. All right.
Yep.
It makes sense, right? I mean, when you ask these questions, right, and if the answer makes sense, you really understand why these things are there, right?
Yeah, for sure.
Yeah. So now I believe you understand exactly what is going on in this analog controller. You understand each aspect of it, and if you are able to make the connections without looking at anything, then you're all set, right?
Yep.
So so remember, you will have access to this control to the connections diagram in the lab. So if you want to use it, you still have it there, right?
Yeah, I always like to look at it at the end because sometimes I notice that we had to connect it to the negative or the positive depending on what op amp we come out of.
Yeah.
So definitely that's something that I always check.
Yeah. Do you understand why sometimes you might need it to connect it on the negative and the positive? You remember why that comes about?
Yeah, it has to do something with doing like positive feedback, right?
Yeah, you want to
Fix
avoid positive feedback.
right. You want to avoid positive feedback, so like if we come out of here and then go here, we would go to the negative, right?
Yeah.
Okay, but if we went if we had like this op amp and then another op amp, then we will go to positive.
Yeah, and then if you have some more sensors in there that reverse the polarity of the signals, then you need another kind of flipping in there. So yeah,
So
depending. Yes.
This one would reverse it. This one is positive, right?
Yeah, because
So
it's just another buffer there, so that it
So
can
what-
stabilize the signal there.
but this one wouldn't reverse it. Would it reverse the
No, that's just a positive one. That one you're pointing to, that's just a positive. It doesn't reverse anything.
Okay,
This
okay.
one does. Most of
This-
them are, you know, inverting amplifiers. That's the term, right? Inverting op amps.
Mhm.
Yeah.
So in this case, this one is because you want to create a difference between the signals, right? So all you really have to do is make one of them the opposite polarity, and it will give you the error. So yeah, this
Okay.
positive or negative in the power amplifier relates to keeping a negative
feedback.
system, right?
Mhm.
I think that's one of the first. You remember one of the first chapters that you did in the lab, checking
Yes.
the polarity of the loop.
Yeah,
Right?
and it went like that. Up.
Yeah, it's a, you know, positive feedback systems are useless, right? They do not give anything to, you know, to your responses. So you want to always keep a negative feedback system, and this relates also to the stability of the main circuit, right? Because you could actually perform mathematical analysis of these analog controllers and come up with some kind of a stability criterion, right? With you remember your electronics courses with the when you study the phase shift and how this relates to the stability of the circuit. It's all here. It's still there, except that we're not really dealing with these fine fine details because it's we just want to study the feedback concepts, right?
Yep.
You're okay, Julian?
Yeah, that makes sense.
All right, guys. So any other questions?
I think that's it. For me, yeah.
What
Julian, you're good?
That's all the questions that we had discussed, but I just wanted to make sure for the final we're gonna be going through one of the labs that we had previously done. And
Yes,
then,
one of the labs that you did in the lab, one of the chapters that you worked on in the lab.
right, and then we're just gonna be asked like concept and actual questions about like what's happening.
About what is happening, you know, after you make the connections shown in the connections diagram for that
Okay.
particular chapter.
Okay.
So you will be, imagine this. Imagine you set up one of the circuits in the chapters that you worked on in the lab, and suppose I just ask you questions about what you are seeing. And I ask you to explain what happens if you change this, what happens if you change that. That is the format that this exam will have.
Okay.
So it will not be any kind of a new material. I will not discuss any kind of new connections. Everything will be there. But what I said last time is, or when I explained to you the format of the exam is, some of the questions that you will see written on the exam will not appear explicitly on the formulated on the actual instructions that you see for that particular chapter. You see what I mean?
Yeah.
Because I will be testing your understanding of what you are seeing. Some of the questions I just, you know, make them more explicit. So for example, question 5 in my assignment, you will probably never find it in the particular chapter that I will ask you to set up, but it will be related to the concepts that you see in that particular chapter. Make sense, Julien?
Yeah, that makes sense.
Yeah, so don't be, you know, don't panic. There will be no surprises, right? Or you will be actually tested on your understanding of the system rather than your ability to follow instructions.
Okay.
This is another thing that I said in the when I last saw you. You remember that?
Yeah.
All right. So we're good then.
Yes.
Yes. Thank you so much.
I'm glad you guys take the chance to, you know, get the most out of this thing, because at the end of the day, it's for you, right? It's not for me, right? It's for your education, right? It's for you guys, right?
Yeah.
Yep.
So you are on the right track. I mean, you guys want to understand this, so the best thing to do is ask questions if something is unclear. All right. So I will see you tomorrow if there are no more questions. All right.
Thank you.
Yeah. Thank you, Professor, for taking the time of your busy schedule to meet with us.
Good night. See you later.
Good night.
Good night.
See you.
Bye.
Bye-bye.